All right. Hello, everyone. Welcome back to Comp 2150, Object Orientation. Or alternatively, welcome back to the class where you do your 2280 assignment that's due tomorrow. It's due tomorrow, right? When is it due? Today? Tomorrow, yeah, 2280 is due tomorrow. Okay, yeah, okay. Whoa, no, sorry. I didn't mean to give everyone panic attacks. Yeah, no, this assignment's not due for a while. 2280 is due tomorrow. I saw there was a lineup in front of Michael's office, and it was unusual to see a lineup in front of Michael's office. So I don't know. It's good. It's good. It's good. It's good. Welcome back. Welcome back, everybody. It kind of feels like this week is going to be a bit of a short week because, I mean, it's no shorter than usual, but we've got the term break, the winter term break immediately after this week, which I don't know about you, but I am looking forward to. I'm looking forward to having some time with no classes. You're all great, and I really love seeing you all, but I don't want to see you for a whole week. Today, I want to spend time talking about our assignment 2. I want to spend some time taking a look at the assignment document itself. I want to give you a sense of what's expected in the assignment. And then as with assignment 1, I want to tell you a little bit about how you're going to be assessed on the assignment, though I'm not going to dwell on it quite as long. You should know at this point from assignment 1 that there is a detailed rubric at the end of the assignment that's being used to assess you. And so I'll let you kind of read most of that on your own. But very directly related to assignment 2, I want to spend a lot of time talking about how you should structure doing simulations. So to give you a bit of a preview of what the assignment is going to look like, you are going to be asked to build a simulation, an event-driven simulation of some contrived sequence of events, and then produce some statistics about it. I want to spend some time today talking in general about simulations, and then I want to go through a worked example of the structure that we're expecting you to do for this assignment. So I'm not going to be doing the assignment in front of you, but I'm going to be doing a worked example that gives you kind of the structure that's expected of what you should do for assignment 2 for this course. Once we're finished that, the topic that I want to finish up is method redefinition. This is primarily going to be a bunch of stuff that you may have seen before, but we're now starting to formalize the terms to describe these things related to method definition. And we're going to be making some comparisons between C++ and Java in terms of the things that you can do with C++ versus the things that you can't do with Java. All right, so assignment 2 is it's a simulation. Assignment 2 is a simulation. I want to spend some time taking a look at the assignment, and then I want to spend some time talking about simulations. So here's assignment 2. This is the PDF for assignment 2 that's posted on the course webpage. The due date is March 1st, so you have approximately 3 weeks of real time to do this. The extra third week is the reading week break. Normally we have 2 weeks per assignment, but this one kind of spans that reading week, so you've got that extra week there to work on it. Similar to assignment 1, we have, this is going to be based on input that you're getting from a file, and we have given a description of the output that you're expected to do. And then we've got some details and expectations about what event-driven simulations are expecting, the kinds of events that you're expected to have, and then other kinds of supporting classes that you're going to do. Submission requirements, and then the assessment of the kinds of things that you're going to be assessed on as output. I'm not going to read all this. I think it's, Olivier wrote this, and I think it's pretty funny. I personally think it's pretty funny, so it's worth your time to read it. But the vague 50,000-foot overview of this is that we're simulating something like Amazon, where we have different kinds of customers, and different kinds of customers get different kinds of preferences in terms of shipping and stuff. And the goal that we're trying to build here is we're going to get a bunch of orders from customers of different categories. We're going to get a bunch of orders of different from different customers where the customers have different categories. And then based upon those categories, we're going to simulate the whole like order and shipping setup. And then what we're trying to calculate is based on the set of customers that we have and the resources that are available to us, which are the people that are working for our company. So how many people we have working for our company, what kind of a profit do we get out of this? And the big goal is really to try and use this simulation. So we're not actually using the simulation to do this, but the purpose of this simulation is to try and maximize profit. So how many people can we hire to get things done quickly so that we get the most profit at the end of the day? The general idea here is that we've got two different categories of customers, Primero customers and standard customers. The ones that are Primero customers have preferred shipping, so they get faster shipping. And if it's not shipped within a certain amount of time, they get a discount on the product that they're buying. These are the learning outcomes that are being used to, that you are demonstrating for this assignment. These are all related to the stuff that we have done in Comp 2150. And then we're asking you to implement a common abstract data type for this assignment as well. The common abstract data type that you're implementing for this assignment is a queue. It's a queue. So it's going to be another linked list, but it's going to be implemented as a queue and a priority queue. The input file that you've got here consists of just a few things: the time that the order arrives, the customer type, so what kind of customer it is that we're trying to build this order for, and then the amount of money that they are paying for that order. And the amount of money that they're paying for the order is related to the amount of profit that we're getting out of this thing. There is a file that's been posted for you to take a look at, file reading example.cpp. We did a little bit of input with cin. So remember, for C++, we have these cin and cout. The file reading example.cpp that's posted beside the assignment description has some examples of how to do input and output in C++ with files, but it still uses cin and cout. So you can read and write files with cin and cout. So to get a sense of what file input looks like for parsing, take a look at the file reading example.cpp. This also does argument parsing, and you probably did this in 2160, argument parsing. You almost certainly did this in 2160. But in C++, it looks a tiny bit different, so you can take a look at that to get a sense of what that looks like. Here is an example of the output from a simulation that's been run. And you can kind of see that this is stepping through time. We're going to talk about simulations in just a second, but there are two major categories of simulations. There are time-based simulations and there are event-based simulations. Despite this saying time over and over and over again, this is an event-driven or event-based simulation. This is not a time-based simulation. Time is something that we're keeping track of in the simulation, but it's not what's driving the simulation. We don't have a clock that's ticking in the simulation. We're just basing the time that events happen based on when we're processing them. So we have the time that an order was placed. So as an example here, we've got time 1, order 1, time 1, order 1, time 1, order 2. So all of these are, they're all happening at the same time. They're all arriving at the same time, or they're starting at the same time. We're not clicking a clock. We're not ticking a clock to move to the next event in the simulation. We're just pulling an event off of the queue that we're maintaining of events that are currently in the system, and then using the time that's in those events, which is just a number value to decide when it happens and what happens with it. The output changes based on the number of additional workers that you have. The example that I want to step through in class today is going to have us just simulate one kind of worker in a scenario that we're going to be looking at. And the goal here is for you to try and build this up to work with multiple different workers. So there's going to be different consumers for this simulation. The details and expectations here this is kind of formalizing what we're going to talk a little bit about today in terms of the structure of the simulation that you're expected to build for this. So we're going to be looking for you to follow a certain pattern for representing the events that you've got. And then the submission requirements are quite similar to assignment 1. So we're asking you to submit everything as a zip file to UMLearn. We're not using Hendon again for this course. And then we've got programming standards, output correctness, and then learning outcomes that are being assessed. And again, I'll give you a chance to read this in your own time. The only thing I'll point out here again is that the queue that you're building has to be your own linked data structure. So this is something you should build from scratch and not just use some of the libraries that are available for C++. Before I get into talking about simulations, does anybody have any questions about the assignment? Yeah. Are you required to use a makefile for this? You're not required to use a makefile. But I don't know why you wouldn't use a makefile. I give you permission, blanket permission, to just take the makefiles that I build and use them. I'm not expecting you to write a makefile. You're not being assessed on writing a new makefile by yourself. There's also this great website called makefiletutorial.com that I really strongly recommend if you're interested in learning about makefiles. I don't know why you would want to do that. I really don't know why you'd want to learn about makefiles. I don't know, but different people are interested in different things. This is a really long tutorial, but it's better than reading the textbook on Make. Because the documentation on Make is I mean, it's really long. It's really, really long. I don't know why you'd read this. I don't know why you'd read any of this. Just take the makefiles that I'm putting together and use those. That's my advice. That's the long way of saying, no, you're not expected to make a makefile, but just use the ones I've been building for you. Yeah.
We're supposed to read the data into a queue and then base the timing off of the queue rather than off of the file directly.
So I'm going to go through a worked example of this in class. The idea with event-driven simulations, though, is that we're not trying to just read the whole file in and then transform it into output. We're trying to read the file in as discrete events. So we read one event and then do stuff. And then we read another event and then we do stuff. And then read another event and do stuff. Yes. So you're going to be doing this in like several stages where you're setting up the queue so it has an event in it. And then you process the event and then read the next thing. And then you may add more events to the queue. And then you process the next event in the queue and then read another line in the file. And then you may do other stuff based on what the events are that happen to be at the head of the queue at any given point. But the way that you're deriving time is basically saying, like, in this case, we've got arrival events, prepare events, and shipping events. The arrival event is like, you know what time it arrived at because that's what it says in the file. The prepare event is something that you are going to say, based on me shipping the last thing, so whatever the time of shipment is for the last thing is when I can start preparing the next thing. And then the time of shipping for that specific delivery is however long it takes to do that. And the way that you're calculating how long something takes is based on the cost of the order. So if it's like a $500 order, it takes a certain amount of time to do. If it's a $200 order, it takes less time to do. Does that sort of make sense? Yeah. I hope that it makes more sense as we go through the worked example rather than me just hand waving. Okay, cool. I think this is, you know, this is dumb, but I think this is kind of cool. I know it's not like, you know, building a 3D game or something like that in terms of simulation, but being able to take the things that we've been learning about just in terms of representing life, representing real things, and then building up a simulation to go through and try and give us some kind of an output based upon that. I think that's kind of cool. And I really honestly wish we could do more of it than we do. But I digress. Let's talk about simulations. So here's your history nugget for the day. Object-oriented programming as a paradigm was originally pioneered in this programming language that's called Simula. Simula, as its name might imply, is a language that was originally designed to build simulations. It was to build simulations and to actually have scientists take these objects that they have in their domain and build up a structure and then be able to run simulations on those domain models so that they can figure out and predict things about what it is that they're trying to study. This started in the mid to late 60s, so O01 has been around for a long time. O01 has been around for a really long time, but it was pioneered in this language. There are two basic kinds of simulations. The first one is a time-driven simulation. And time-driven simulations can be done in a couple of different ways. One way is to set up a clock that your entire system is run around. So you have, as part of your simulation domain, something like a clock class. And what happens with every tick is that you're trying to simulate all of the things that happen within the period of a single second or a single unit of time. And you keep ticking that clock and processing your events and ticking the clock and processing the events and ticking the clock and processing the events that are supposed to happen at some point in time. The other way that time-driven simulations can happen is that you just use real time to represent things in your system. One of the assignments that I like to give in operating systems is to do a simulation of a scheduling algorithm. So our operating system, when it's running, there are many different programs running all at the same time. And we have this illusion that they're all running at the same time because they're actually all just taking control of the processor for short bursts very quickly. So they're switching back and forth between processes very, very quickly. And part of the operating system's job is to decide which program gets to use the CPU next. This is called scheduling. You can simulate scheduling by having processes in your system that's just like a thing in your code that you write that just goes to sleep for a certain amount of time. So you're taking advantage of real-time passing. It's not doing anything, but it's pretending as though it is something that's happening. And then at the end of your simulation, measure things about the system that you've just created. So measure things about the algorithm that you're testing, even though the code isn't actually doing a real simulation of processes running. Time-driven simulations are good. They're good because they give you a sense of time. They give you a real sense of time, and you can use things like a clock that's either on your system or something that's as part of your domain model to measure progress. But it's not a universal way to do simulations. And the other kind of simulation that we're going to be taking a look at is event-driven simulations. And the idea with event-driven simulations is that we're going to actually take the time to model out different events that can happen in our system, and we're going to be processing events as they appear in the system, as opposed to trying to measure time and use clocks to do our simulation. An event-driven simulation has this general idea of that we're going to keep a queue of events. So we're going to have to model a bunch of different kinds of events that will happen in our system. And we're going to keep track of which event is supposed to be processed next in the system by maintaining a priority queue of events that we have. The priority that we're using in the systems that we're talking about right now is time. So the lowest amount of time, the lowest time when this event is supposed to happen is the highest priority item in this queue right now. Generally, we're going to pop an item off of the queue. This is mixing together ideas. We're going to, oh gosh, what is it? Unshift. We're going to shift an item. DQ, that's what we're doing. We're going to DQ an item off the queue. And the item that we DQ off the queue is the highest priority item. We take that item off of the queue and we process it. And processing that highest priority event will probably yield some kind of changes to our system. The changes to the system can be either we're going to make changes to the domain models that we have for the thing that we're simulating, or more events will be generated, or both of those things will happen. So we pop something, we take something off the front of the queue, we process it, we change our system, we maybe make more events, and then we go back and we take the next thing off the queue, and we process it, and we maybe make changes to our system, and we maybe add new events to the system, and then we take the next thing off of the queue, and we keep doing this until the queue is empty and there are no more events for us to process. Here's what I want to do. I want to work through an example of building up a simulator for a Pokemon Center. I'm gonna beat Pokemon to, oh no, that's the wrong way to say this. I'm gonna keep using the same Pokemon examples over and over and over again. And I'm half sorry that you get tired of them, and I'm also half not sorry that you get tired of them, just because it's, I think it's fun. So if you remember, we have this idea of this world where we've got a trainer, and the trainer has Pokemon. And as they go through this world, they battle their Pokemon against other Pokemon. Sometimes it's wild Pokemon, and sometimes it's other trainers that they're battling against. Each Pokemon has a certain amount of health, or it can be afflicted by different things. So Pokemon can be burned, or they can go to sleep. But eventually what happens is they faint. They run out of health because they've been in a battle and they just ran out of health, or some other situation has happened to them. And you have to take your Pokemon to a Pokemon Center, or you can take your Pokemon to a Pokemon Center. And this is a little building that has a character called Nurse Joy. Nurse Joy's assistant is Chansey. And the idea is that once you get to the Pokemon Center, you give your Pokemon to Nurse Joy and she revives them. She heals them all up. I want to give an example here of simulating wait times at a Pokemon Center. So in the game, it's just you when you're just playing on the Game Boy. It's just you. You are the only real person in this world. Everybody else is just a figment of your imagination. In real life Pokemon, you'd go to a Pokemon Center and there would be a lineup. There'd be other trainers there waiting to get their Pokemon revived or healed by Nurse Joy. I want to go through the process of simulating wait times. So approximately how long does somebody have to wait once they arrive at the Pokemon Center to get their Pokemon healed so that they can leave and keep finding wild Pokemon and trying to become the best, the very best, like no one ever was. Here's the setup. Our domain model is that we have a queue of trainers. This is our Pokemon Center. We have a queue of trainers that are waiting around to revive hurt Pokemon. There's only one nurse per Pokemon Center. So there can be a bunch of trainers waiting around to revive hurt Pokemon. And remember, we can have a max of 6 Pokemon on our person at any given time. And this is that's the highest number that we can have to give to the nurse. But there's only one nurse per Pokemon Center. So that means that there could be a situation where we have multiple trainers waiting around while one of them is having their Pokemon revived. Because there's only one nurse per Pokemon Center, that means that only one trainer at a time can have their Pokemon revived. Every trainer that comes to the Pokemon Center has a different number of Pokemon. And this is just because some of them are more experienced and they've got a better roster, and some of them are less experienced and they just don't have that many Pokemon. Maybe they just come from Professor Oak's house, and I've been talking to Gary, and yeah, I don't know. Each trainer has a different number of Pokemon, and the idea here is that the work that Nurse Joy has to do to revive each of these trainer sets of Pokemon is going to take a different amount of time. So it's not uniformly, it all takes 5 minutes. That wouldn't be a very interesting simulation to run. They're going to take a different amount of time per trainer that we have in this system. The goal that we've got is that we want to determine the average wait time for a trainer at this specific Pokemon Center. And to do that, we're going to run a simulation that will go through this process of using events to drive the whole simulation forward, so we can take measurements about how long each of the trainers have to wait at this Pokemon Center. We okay with that? This seems good. This seems like an okay idea. That's good, because I'm not going to change it in the middle of the lecture. As always, I want to start by doing a little bit of design. For the record, I'm not going to code this up. I'm not going to code the simulation up. I just want to step through the way that this is supposed to work, but I still want to go through the process of designing this system before we start working through how it's going to work. We have 3 different kinds of events that can happen in this system. The events that can happen in this system are that a trainer can arrive at the Pokemon Center. They can, burst through the door with their Pokemon. Please help me. All my Pokemon have fainted and I need them to get revived or healed. We have a service event. This is when Nurse Joy is actually able to see the Pokemon and help revive them. And then we have a departure event. And this is when Nurse Joy has finished reviving the Pokemon and that Pokemon trainer is able to leave the Pokemon Center. We want to model all of these things. We want to model each of these different events, and we want to model them separately. We want to model trainers separately from this whole idea of events. We want to model trainers completely separately from this whole idea of the events that are being used to drive the simulation. We're going to be modeling trainers and the Pokemon Center, the queue, as something that is separate from this queue of events. We're going to have 2 queues in the system. We're going to have a queue of the trainers that are waiting for Nurse Joy at any given time. And we're going to have a queue of events that are currently happening in the system. The events that have yet to happen, the events that are currently happening. And the events queue is what's going to drive the simulation. The model of trainers in a separate queue is going to be what we're using to sort of maintain state about this system at any given time. It's really compelling. It's really, really compelling to just take the input file and then think about this as a transformation that you're doing on that input file. It's really compelling to think about just reading the input file, doing stuff to the whole input file, and then spitting an answer out at the end. We don't really want to just transform or process an input file. Our goal here is to model the system. That really fell flat. I want to do that again. We don't want to process or transform an input file, and we want to model trainers separately from the whole set of events. Okay, now why though? Why though? Why do we care? Why do we want to do these in separate events? Why do we want to model the simulation stuff, the arrivals, the service, the departure events? Why do we want to model the trainers? And why do we not just want to take an input file and then process it and then spit out some answer? A simulation is about modeling your system. It's very much about modeling the system that you're trying to study. We want to model 2 things. The system, which is the Pokemon Center, In other places, this could be your algorithm. In other places, this could be your scheduling policy. In other places, this could be something. You've got some domain that you're trying to model as part of running this simulation that it can stand alone all by itself. The other thing that we're trying to model is events that are happening in and to the system. The events that are happening in this system are arrivals, service, and departures. These are two completely separate concepts. Yes, they are related to each other in the sense that the arrivals, the service, the departures, these have to be happening to the Pokemon Center, but the Pokemon Center doesn't have anything to do with this event-driven simulation stuff. One way that you can think about this is to start thinking about this as data, which is our Pokemon Center, and metadata, which is the events that are happening to the Pokemon Center. These are completely separate concepts. We don't want to just take an input file and then spit out a bunch of output. We don't want to take an input file and process it and spit out a bunch of output, because ideally what we can do with this design, having our trainers and the trainer queue, which is the Pokemon Center, and all the events that are separated from that, ideally, we as scientists can make this simulation and contrive the simulation in the ways that we want to make measurements about. That means that we can do things, or that we should be able to do things like, let's try to do a simulation where the Pokemon Center is busy to begin with. The trainer queue is full already. There's a bunch of people here, and now there are new events happening to the system. I don't have to build an input file that makes this situation happen. I just do that model. I put my system in that state from the beginning. I want to know what happens if I have a Pokemon Center that has multiple different nurses that are able to work at this Pokemon Center. I can't just have a file that says there are multiple different nurses and then start trying to process the file. But if I change my system just a little bit and I have 2 queues instead of 1, I can start to do things like that. These are separate concepts. They are separate things. They are related to each other, but they're not part of the same domain model. They're not part of the same domain model. Here's an example of the kind of input file that I might expect to see for a simulation problem like this. The input that I would expect to get will tell me about the time that an arrival event happened. It will tell me what kind of a thing it is. In this case, the only thing that we're going to model in this simulation is arrivals in terms of inputs. And the other thing that it's going to tell me is each of these trainers have a certain number of Pokemon, and that amount of Pokemon is used to figure out how long Nurse Joy has to work with that trainer to revive all of their Pokemon. So the sample input here is that we have an arrive of a new trainer happening at time 10, and that trainer has 3 Pokemon. We have another arrival of a trainer at time 11, and they have 6 Pokemon, so they've got the maximum number of Pokemon. We have another arrival that happens at time 14, and that trainer has 2 Pokemon. This is the kind of input that I would want to get for a simulation like this. I'm going to break this down into a few different parts of pseudocode. I want to run through this simulation kind of at the high level. And we're going to take a look at each part of this in turn. At a really, really high level, the steps that I'm going through here are to initialize my trainer and events queue. So I have 2 separate queues. One is the queue of trainers. This is empty to start. There are no trainers in my Pokemon Center at the beginning for the simulation that I want to run. If I want to try creating a simulation that's busy already, I would start by initializing this queue to a bunch of trainers in it already. I want to initialize my events queue. this is my priority queue, the events queue. I want to initialize this one to be empty because I'm going to start loading events into this queue one at a time. The very first thing I want to do is begin to prime my set of events. So when I'm using the word prime here, what I'm saying is I'm going to have outside of my loop a single kind of block of code that's going to read one thing and insert it into the queue so that when I start doing this loop over the queue is not empty. So there's something there to start with. I'm going to read the first line of input, the first arrival, and I'm going to put a new arrival event. So I've got this model, domain model object of an arrival event. I'm going to put that arrival into the queue, into the events queue. And then I'm going to loop until there are no events left in my system. Within the loop, I'm always going to take the highest priority event. This is the first thing that has to happen next. This is the thing that has to happen next. And then I'm going to process that event. And part of processing that event is either going to be changing the system state. So I'm going to change the queue of trainers that I have, or I'm going to add new events to the system that are using this as a kind of a basis, or I'm going to do both. So I might change the state of the system and I might add new events to the system. I'm going to keep spinning here until I have processed all of the events. So I'm going to keep adding new events to my system based on what I'm getting as input for the state that I'm working, or the event that I'm working on right now. But eventually there's going to be nothing left in the system. Eventually there will be nothing left in this system, and then I can stop and I can print the statistics out of what I have calculated about running this simulation. In terms of this inner part of the loop, process the event, I've got 3 different kinds of events in my system, and I have to do different things for each of those kinds of events. When I start running this simulation, there's going to be an arrival event. So there's going to be a trainer that has arrived at the Pokemon Center. That's the first thing that I'm going to have to do in this system. The very first thing that I should do is to dequeue that new arrival event that I've got in the system. I'm going to take the trainer that's arrived into the Pokemon Center, and I'm going to just blindly add them to the queue. The queue that I'm adding them to here is the system itself, the Pokemon Center queue. And then I'm going to ask a question. If Nurse Joy is available, so she is available for a trainer to go immediately to the front of the line and she can start healing and reviving that person's Pokemon. If Nurse Joy is available, then I should create a service event for that first trainer. I should remove that trainer from the queue because they're seeing Nurse Joy. They don't need to wait in line anymore. They can start working with Nurse Joy immediately. And I should add that new service event for that trainer to the events queue. So I've dequeued the arrival, and I've added a new event to this events queue that is for Nurse Joy is going to start healing and reviving these Pokemon. If there are more events in the file, so if there are still more lines of input for me to read that represent more arrival events, then I should read the next line of input and add that new arrival to the events queue. So to say that this new trainer has arrived. If there's one trainer that's been added immediately to this queue, which there was at the beginning of our setup, we've created this new service event. As we dequeue a service event, what we should do is, this is basically saying Nurse Joy is going to see you now. Nurse Joy is going to see you now, and she's going to heal and revive your Pokemon. We're going to take that service event, and we're going to remove it from the events queue. And then from that, we're going to generate a new departure event. We're not modeling in this simulation Nurse Joy actually doing any work. We're just modeling in this simulation when she's going to be done. So the departure event says this is the time at which the trainer is going to leave because Nurse Joy has finished healing and reviving the Pokemon. The departure is going to be whatever the current time is. The current time is the time that you just pulled off of the queue. So the time of the event that you just pulled off the queue. Plus the number of Pokemon times 2 minutes. So let me step back up here. We're going to add this first arrival event to our queue, and the arrival event happens at time 10. When we pull this arrival event off, we're going to go through this process of creating this new service event for that first trainer. And the service event is going to have the same time as the arrival because this trainer is just going to skip the queue and go directly to talk to Nurse Joy. When the trainer talks to Nurse Joy, the current time is whatever the time is for that service event. So Nurse Joy can see you now. This is the time that she's going to see you. This is the time when you're done. So the current time of whatever the service event is plus the number of Pokemon times 2 minutes. It takes 2 minutes to revive one single Pokemon. You add this departure event to the events queue. And the idea is that this is a priority queue that you're using the time that the event is supposed to happen as the priority. So the lowest timed thing is what happens next. And when this trainer is done seeing Nurse Joy, so this is you popping something, taking something off the front of that queue that is a departure event, then you're going to inspect the queue that you have of trainers. So this is not the events queue, but the queue of trainers that you've got. So this is the number of trainers that are waiting in line. You're going to take the trainer that is the one that's been waiting the longest, which is the one that's at the front of the line. You're going to create a new service event for that first trainer. And you know that Nurse Joy is available immediately after this departure event is being processed because that trainer is leaving right now. So you can take the time of the departure event, and that's when the next service event is going to happen. Okay, so I think, rather than me standing up here hand waving what all of these things are supposed to be, a better way to do this would be to try and represent it visually to get a sense of what the queues actually look like as we're working through this system. But I need to take a break. I need to take a breath. How many people are going to that Valentine's thing today? Some of you? What, Valentine's thing? Is nobody going? Oh no. Dev Club and CSSA are putting on like this Valentine's Day event. Have they not advertised this to anybody? Ah, okay. Well, 2280 tomorrow, okay. Where are your priorities, people? Assignments, parties. It's a bunch of CS people. What am I saying? Ouch. Yeah, I'm not going to that party. Rob, do any of you know Rob? Do any of you know Rob? Do any of you know Rob? Well, I'll try and sell it to you then. Rob's going to be there. That's not the end of the story. There's a talent show, and Rob's in the talent show. And Rob is a volunteer firefighter. Rob's a volunteer firefighter. And his talent, the thing that he is, this is what he's told me. So I don't know if I'm spoiling anything, but this is what he's told me. He's bringing his gear with him, and he's going to show how fast he can put it on. Because that's something you have to do when you're a firefighter is get dressed real fast. Get dressed real fast. And I've seen him do this before. That's not weird. I've seen him do this before. And I've seen him put his firefighting gear on. And it's impressive. It really is actually quite impressive to see how quickly a firefighter can get their stuff on. So I don't know if I've convinced you to go, but it might be worth checking out. I'm also not going to be there. I'm not going to be there. I don't know if that's even more compelling or not. Okay. So I want to take the time to step through this. I've tried to annotate this a little bit. Partly to keep myself on track, but also partly to try and keep this all in a single document so that when I share this with you, you can kind of see it all together in the same place, as opposed to across 3 or 4 different slides. I want to take you on a tour of what this is, what these different parts are, and what my chicken scratch says, what my writing says. I believe that it's fairly readable, and I'm standing back kind of far, and I can still read it, but it's my writing, so of course I can still read it. On the left side, I've written in big letters, simulation, exclamation point, because that's what this is. This is a great big simulation. I'll make it green. It's a simulation. Okay. What I've got here is I've got inputs at the top. This is that input file. So if I go back to my slides, this is the input file that I've got. I've just transformed it into a table so that it's a little bit more visually appealing. Here, this is going to be my Pokemon Center. This is where trainers are going to be waiting for Nurse Joy. This is the queue of trainers that are currently waiting to see Nurse Joy. Here is going to be the queue of events that I have in my system right now. So as I'm going through this, I'm going to be making changes both to the trainer queue and to the events queue. The events queue is what's going to be used to drive the simulation. So this is what's going to be responsible for causing changes in the system to happen and having more events being added to the set of events that are going to be processed. The very first thing that we have to do before anything is, as we start the simulation, we have to prime the events queue. We have to put something in there so that when our loop starts running, there is an item to pull off the queue in the first place. The events that I have are going to be processed differently. An arrival here is going to ask the question, is Nurse Joy currently available? So are there no other trainers waiting around in my system for help? If there's no other trainers in the queue, so if that queue is empty, then I can create the service event. This is me doing a little bit of an optimization to say, I don't really need to add the single trainer to the queue by itself and then immediately pull it off to make a new service event. I'm just going to put them and say that Nurse Joy is going to see them now. If Nurse Joy is not available, so somebody else is currently seeing Nurse Joy and having their Pokemon revived, then we need to add that trainer to the queue. We need to add that trainer to the queue of trainers. So add them to the queue for Pokemon Center. After we've done that, we've processed this arrival event. Now we need to read the next line of input, and reading the next line of input will almost certainly add another arrival event to the system. When we're working with these service events, what we're doing is, this is basically saying Nurse Joy can help you now, and you're going to start seeing Nurse Joy. And what you're doing here is creating a departure event, which is measured as the current time plus the number of Pokemon that you have times 2 minutes. When we're processing a departure event here, we're going to then just remove a trainer from the queue of trainers. So the next person that's waiting in line, they get removed. And we can create a service event for that trainer. So we take the first trainer off the queue and we create a service event for them immediately after they have been removed from the queue, which is using the current time. Nurse Joy is finished with this trainer. She's now able to see the next trainer. So let's start. The very first thing that we have in this file is an arrival at time 10 with 3 Pokemon. So when we're starting our simulation, we're priming our events queue with the first line of input. And when we're reading a line of input from this, we're modeling arrivals to the system. So I'm going to add a new arrival. I'm going to call this one trainer 1, so T1 here. This is trainer 1. Trainer 1 is arriving at time 10. And they've got 3 Pokemon. The time here is an absolute value that we get from the file. So when it says that their arrival time is 10, that's the first arrival time is 10. So we've primed our system. This part is now finished. We've done this. We've primed the system and we're ready to start running through this loop. We've got something in our queue so we can start doing stuff with it. The first event that we have in our queue is an arrival event. We've got this question here, is Nurse Joy currently available? Nurse Joy is currently available. There are no other trainers in the queue. Nobody's waiting around to see Nurse Joy, so we can just immediately go to see Nurse Joy. So yes, Nurse Joy is available. So what we're going to do is create a new service event for this Pokemon trainer. So I'm going to scratch off this one. We've dequeued this event from the system, and we're adding a new event to the system, which is that T1 is going to have Nurse Joy help out with the Pokemon that they've got. So trainer 1 is having their Pokemon healed and revived. The time that this service has is at time 10, and there are 3 Pokemon. The service just happens immediately at arrival time. So we take the time of the last event that we processed, and we're using that as the start time for this thing that we've got. We insert this back into the queue with priority, but the priority here is that, well, there are no other things in this queue, so it just goes right to the front. It goes immediately to the front. The second thing that we do with an arrival event is that we get the next line of input from the file, provided the file is not, we're not at the end of the file. So we finished with this one. Here's the next line of the file. The next line of the file says that another trainer has arrived at time 11. So I'm going to add a new event to my queue here. This is now trainer 2. It's an arrival, and it's at time 11, and they've got 6 Pokemon. And then that's the end of this iteration of the loop. So we finished working through that one event, which was the first arrival event in the system. Now we go back to the top of that loop, and we dequeue the highest priority thing in our priority queue. The highest priority thing that we currently have in our priority queue is this service event for trainer 1. It has time 10. It's the lowest time. So Nurse Joy can see you now is what we're saying. Nurse Joy can see us now. And what we do with this one is we say we create a new departure event. And a departure event is taking the time that we have for the service and then adding to that the number of Pokemon that we have times 2 minutes. So I'm going to remove this from my queue. And I'm going to add a new item to it. This is for trainer 1. And we're going to have a departure event. the time that the departure event happens is time 10 times the number of Pokemon that we have, which is 3 times 2. So the time is 16. And we could still put that we got 3 Pokemon here. We could still put that. This gets inserted into our queue of events at the end here because it has a lower priority than the arrival event. So because it's something that's happening after the arrival event, the time is 16, it gets inserted with a lower priority. I'm going to erase these. I'm just going to move some of this stuff up. So that's the current state of our queue. We have an arrival, and we have a departure. We've now finished processing this service event. So we're going to go back to the top of our loop. At the top of our loop, we have an arrival event. And so now we have to ask the same question. Is Nurse Joy currently available? Nurse Joy is not currently available. Nurse Joy is not currently available because there is a service event that's happening. So we've got a departure that's in our queue. Somebody is being worked with right now to have their Pokemon revived. Nurse Joy is not available, so we're going to add a new trainer to the queue for the Pokemon Center. The trainer that we're adding here is Trainer 2. So we're putting this trainer into the queue of waiting trainers. These are the people that are currently waiting around in the system for Nurse Joy to become available. This isn't a priority queue. It's not a priority queue. It's just first come, first serve. Whoever was here first is going to be the next one in the line to get service, to get their Pokemon healed from Nurse Joy. So we've processed this arrival event. And now what we have to do is we have to read the next line of input from this file. So I'm going to cross this line out. We've removed this arrival event because we removed it from the queue itself. So by processing the arrival event, we're pulling that thing off the queue, we're removing it from the queue, and then we're changing the state of our system by adding a new trainer to the queue of trainers that are waiting around to get some help from Nurse Joy. We read the next line from our file, which is Trainer 3. Trainer 3 has an arrival, and the time is 14, and they've got 2 Pokemon. I'm going to have to reorder my queue here. This is a priority queue. The priority that we're using here is the time that the event is supposed to happen. So I'm going to do this. I'm going to erase the arrival event for Trainer 2. And I'm going to move the arrival event for Trainer 3 up on top of the departure event for Trainer 1. All right. So now we're finished with that last line of input. We've finished processing that arrival event. We're going to go back to the top of our loop. Our queue of events is still not empty, so we're going to start processing things again. The next event that we're processing here is this arrival event. So this new trainer has arrived before the departure of the first one. We check to see, is Nurse Joy available? Nurse Joy is still not available. So what we have to do here is add that trainer to the queue for the Pokemon Center. So we'll remove this arrival event. And I'll put T3 here, Trainer 3 at the back of the line. There are no more lines of input from my input file. There's nothing else for me to add to this system, so I don't create any new arrival events in this system. There's nothing left for me to do there. This is now finishing that iteration of the loop. Yeah, yeah. After each iteration of the loop, you're kind of like leaping forward in time to whatever the time for the next event is in the system. So what we were just doing time 14, which was the arrival of the last trainer. And then now that we go to the next iteration of the loop and we pull this one off, we're kind of time shifting to time 16. So again, we're not ticking time and keeping track of what event happens at any given time. We're just saying this event happens next. And when that event happens, it's time whatever. So it's time 16 in this case.
So the time is sort of tracked between the difference of in arrival, their surface.
Yes.
And when they get their surface.
Yeah. So what we're going to calculate at the end here is at the end of an actual departure here. In the system for our Pokemon Center, we're going to want to make sure that we keep track of when the trainer arrived to begin with. So I haven't been putting that in here, but this whole system that you have here with trainers and when they arrive, you would also want to model when they arrived in the system so that you can take the difference of when the departure event happens and when they arrived in the system in the first place.
Yeah,
Yes, exactly. So add them all together and divide by the number of events in this, or the number of trainers that you have. Yeah, good, good. Okay, so we just finished the arrival of the last trainer. Now we're going to go through the process of pulling the next item off of our events queue, which happens to be a departure. The departure here, the way that we work from this is that we're going to remove this from the queue. So I'm going to cross this off for now. And then we're going to do kind of what we were just talking about here. So we're going to take the difference of when the departure event happens, which is at time 16, and the arrival event for that trainer to calculate how long they've actually been there, how long they've been waiting for work. They were able to leave, I don't know, 6 minutes after they got there. They show up, give Nurse Joy their Pokemon, and then they're immediately out of there because they were first in line. After we do that, after we've removed this trainer from the queue, from the events queue because of their departure, now we have to remove a trainer from the queue that is for the Pokemon Center itself, which is the next trainer that's going to have work done for them. So we're going to take T2 off of here. And we're going to create a service event for the next trainer. So I'm going to rewrite that because I can't even read that. We're going to create a service event for the next trainer. And the time that we're going to use is the time that that last trainer departed. So I'm going to put a new event in here. There's nothing else, so it just bubbles to the top of the priority queue. And the time that they get served by Nurse Joy is at time 16. And this trainer had 6 Pokemon. So we can look back in our file here to see that they had 6 Pokemon for trainer 2. And now we're finished with that event in the system. So we finished that departure. That first trainer that got there has left. We've added a new service event for the next trainer that was waiting in the queue by removing them from the system. And all we've got left in here is a service event. We'll process the service event. So we're at the end of that loop. We process the service event. We create a new departure event. So for trainer 2, this is still the only thing in here. So departure is going to be at the current time plus number of Pokemon times 2. So we've got the current time is 16. The number of Pokemon times 2 here is 12. So the time is 28. And I'll just put 6 here to represent the number of Pokemon that we've got. We're finished with that. We go back to the top of our loop. We process the next departure event. And I'm going to stop. I'm going to stop because I think we're okay. I think we're okay in terms of what's going on here. I'm going to pause. Just going to pause. We'll keep going through this process until Our events queue is empty after we've processed that last event. The events queue will become empty after we process the departure event for trainer 3. The events queue will become empty because the trainers queue will be empty. There's no more Pokemon trainers waiting in the lineup anymore. There's no more arrival or service events to add to the system. There are no more departures to add to the system because all of the Pokemon trainers have departed from the system. And then we can shut down the simulation. Everything's finished. Yeah.
Given the amount of moving parts
Wouldn't the, sorry, can you repeat that?
wouldn't the be just
The header for the while loop, like the condition that you're testing on?
so many?
It's not. There's actually only one condition that you're testing for the while loop. The only condition that you're testing for is this is not empty. There will always be events in the system if there are trainers in the system or if there are more lines of input to read based on the rules that we're following here. At the end of an event happening, we're either going to add a new thing because there's more lines of input to process, or we're processing an event that causes another event to happen, or we're done and we don't add anything new to it. So we'll either take something off or add something new. But the whole thing is finished when we have no events left in our events queue. So the condition is quite short. It's basically while not empty events queue. Yeah. Does that make sense? Yeah. There are some conditions, there are some invariants to your system that you can start to think about. So if you model these two things together, one invariant that you have is that the events queue should never be empty if the trainers queue has trainers in it. It can't be. It shouldn't be. It shouldn't be. If there are trainers waiting to see Nurse Joy, then there has to be an event that gets added for that trainer. There must be in this system. Otherwise, you get to the end and there's just that last trainer, like, hands in pocket. I don't know what to do because Nurse Joy isn't seeing me. My Pokemon still need to be healed, and she's gone home for the night. She's gone home for the night. But the way that we're looping on this is just always loop until there's no events left in the system. Okay, keep going. We're good. This video, of course, is recorded. I mean, I actually have no good sense of when my voice hits somebody's machine sitting at home, because I can go back to my office after this class and I can open up the stream and it's still going. So I have no sense of when it finishes. And that's part of the reason why I turned the chat off. And I don't know how people do that. The main reason I turn the chat off is because I can't answer chat while I'm trying to do stuff. I'm going off the rails here. I'm really going off the rails. I can't answer chat while I'm doing stuff, but I think there's some kind of way to change it so that it's faster, but yeah.
Would you have a chat if it was
Would I have a chat if it was a paid donation? So like, should I sign off on this? Like, you know, make sure to click that subscribe button and like click the bell for notifications, and don't forget to pay my Patreon or whatever and buy me a coffee and all that stuff. Your tuition pays surprisingly little of my salary. It pays surprisingly little of my salary, but I'll take that as the coffee you're buying me is the tuition that you paid. Yeah, yeah. So no need to subscribe. So this is recorded. It's on YouTube. I will put this diagram in the state that it's in right now. I realize that it's kind of like in this complete state, but the way that it's changed is available to you on the course on YouTube, and then this document itself will be available to you on the course webpage. Okay. So we've got about 5 minutes left, and I kind of just want to quickly get through some of this stuff. some of this stuff is definitions. Some of this stuff is definitions and adding names to things that you have maybe seen before. Some of this is like weird stuff in the way that OO as a concept works. And it's best shown by example. In these cases, I'm not going to do any coding. I've just done the coding already, and I just want to show you what these things look like when they run to see the behavior that happens. So we're going to spend a tiny bit of time here talking about replacing methods. When you're building subclasses and hierarchies of classes, there are a couple of ways that subclasses can change the way that their parents look based on method names and method signatures. There's stuff that we know about. You can extend a class, and then you can do no changes to the set of methods that they have. Your parent has a super interface. Your parent has an interface. You extend it, and all you do is add instance variables. I don't know why you would do that, but it's something that you could do. You can add new methods, which is basically saying my parent has an interface. It has these methods. I'm going to extend that, and I'm going to add behavior to this thing. I'm going to add more methods to what's there already. There's also going to be ways to replace a method from a superclass. And there are 3 names that we're going to give to this: shadowing, overriding, and redefining. And then there's ways to refine methods from the superclass, which is starting to use that super keyword in Java to call methods from the superclass and then change the behavior of that method definition. We're going to talk about replacement of methods from the perspective of shadowing. I'm not going to talk about the replacement of methods in terms of overriding, because this is stuff that you've just done over and over and over again. This is the stuff that you're familiar with in terms of hierarchies. And redefinition, we're going to be talking about this in the context of names that you can apply to the ways that methods can be redefined, even though they look very similar to the parent's class implementation of this. So first things first, this idea is called shadowing. Shadowing is something that you can do in Java, but you have probably never done it yourself. You've probably never done it intentionally yourself, but it's an effect that you may have seen before. Methods in Java cannot be shadowed. This is not an option that you have in Java. Instance variables in Java can be shadowed. So you cannot shadow methods because polymorphism is always on, but you can shadow instance variables. Here's my example. You've got 2 classes. You've got a parent class and a child class. The child class extends the parent. Shadowing here of instance variables is that both the parent and the child have a variable that is named the same and has the same type. So in my subclass, child, this variable that's called value, shadows this variable that's called value in the parent class. In Java, we cannot shadow methods. Polymorphism is just always on. You will get the behavior that you are familiar with and expecting to see when you call a method on a class that's an extension of a class. Here's this similar structure, but with values attached to it to demonstrate to us the idea of having these instance variables shadowed and methods being overridden and not being shadowed in Java. So I've got parent and child here. In this case, I'm giving a value to parent that is 37 for value, and I'm giving a value to child, which is 7. They have the same name. Of course, you should never create public instance variables like this. It was just kind of for demonstrating the purpose of what we're talking about here with this idea of shadowing. And then I've got a main method here. So a main method creates 2 instances of these classes, one parent and one child. We print out the values that the variables have that are shadowed. We call methods to show that we have polymorphism here. We change the dynamic class of P to be the subclass, but the static class remains the same. And then we call methods on those again. I'm going to run this, and this is where we're going to end today. So we've got this output from the beginning here, p.value and c.value. This is what we expected to see, what I expected to see when I saw this. When I print out p.value, I get whatever is defined in the parent class as the instance variable. When I print out c.value, I get whatever is defined in the child's class as the instance variable's value. The value that I am getting out of here is tied to the static type of the variable. So P has a static type of parent, so it gets this value variable from the parent class. C has a static type of child, so it gets this value from the child class. I call the methods, and when I call the methods, it's printing out what I expect. I'm getting polymorphic behavior here. P is invoking the method on parent, and C is invoking the method on child because that's what the types are at runtime. When I change the dynamic class of P to be child, so I say P is equal to C here, I'm still getting out 37 here as p.value, and its c.value is still going to be 7. But the values that I'm getting from the methods are now going to be both from the child class because we're getting that polymorphic behavior. And with that, I've stolen 30 seconds of your time, so I'm really grateful that you're giving me that time. We will come back here next class. And that's it. I'll see you on Thursday. Bye, everybody.